Alright, so static fluid, even though the particles in the fluids are moving, but the center of mass is not. That's what we call static fluid. When there's wind blowing, all the velocity will be going a little bit more to the direction of wind. They are all moving in different directions still, but together they can have a center of mass velocity. That's what happens when the wind is blowing. But when there's no wind, we call it static fluid. Now, because these particles are bouncing around, they will bounce into a surface if there is one, and then go away, and that will create a force on the surface. So when you look at a bottle of can, you see it's like nothing's happening, but the particles in the air are very busy hitting the wall of this can. So there's actually forces from air on this can right now. And there is forces from air on you right now, even though you don't feel it. The reason that you don't feel it is because you are used to it. It's like if you have a watch you wear it every day, you kind of forget it, you kind of don't feel it anymore. Air is even more consistent. You might need to take off your watch sometimes, but air is always there since the day you were born. So you are always feeling this force from the air, and you just forget about it, and you just get used to it. To show you that air is actually pushing us, I'm going to remove the air inside this can. Right now, there are air both outside and inside the can, so the force they push on the wall cancels, and the wall does not get a net force going in or out. If I chase away the particles inside the can, then there's only going to be forces from air outside the can, and you will see the can will be crushed by the force of the air. To chase away the waters, to chase away the air, I'm going to heat the can. The water particles, the air particles will be chased away if I heat the can, so that's why I need a fire right now. So I'm going to heat the can to chase away the water, to chase away the air particles. Right now, the air particles inside the can are feeling really hot, so they are escaping from the opening. And now, if I manage to close this opening before they come back, sorry. All right, let me try it again. So my plan is to chase away the air particle inside the can, and then close the opening with water before they have a chance to go back. Let's wait a little longer to make sure all the particle is out of the can. Let me try again. Okay, now I see the particles are moving out of the can. Do you guys need to see that again? Let's try one. So this is how big the force from the air is. You can, I'm not crushing the can with the clamp. It is the air that is crushing this can. Alright? And the reason you do not feel that right now is because you're just used to this force. Air is crushing you right now, but your body is strong enough to endure this pressure because you are born with this pressure over there. But if you remove the air inside the can, this is how big the force that the air is applying to the can right now. Yeah, Jackie?
Is that the same effect and the reason why if you go super far down underwater, I mean, yes, there's the pressure from the water, but why, like, something could implode underwater?
Something will be crushed underwater.
Yeah, because there's no water inside so it's not used. Would it be a similar effect?
So let's say submarine. So a submarine getting into the water may be crashed if it goes too deep. Now I'm going to show you that this force from fluid will become bigger if you go deeper. And that's why the submarine is fine in the air, but it will be crushed under deep water. Okay? So just like the air can produce force, water can also produce force on an object. When you throw something into the water, force is applying a force. Air is applying a force. Similarly, water can also apply a force to you. Water are also fluid. There are water particles bouncing around, bouncing off the surface. So it can apply a force on the object. So this force from the water is the reason that things can flow in the water. Right now, even though it's not a sphere, I asked for a sphere, you give me a sphere. There's force from the top of the ping pong ball from the air. But water below the ping pong ball also can apply a force. And remember, there's also gravity. So these are all the forces acting on this block. Now, you can see this ping pong ball is floating. If I throw another ping pong ball, it's also floating. If I stick them together they are also floating. But when I stick two stuff together, when I stick two objects together, the total gravity acting on this combined object should be bigger because now the total mass of the system is twice as big. But it's floating in the same height. This means that right now, the force on this big object from the air should also be twice as big. Same for the water. The water right now must apply twice as big as the force when you have a bigger object. What exactly of this object is bigger? Is the area up here and the area down there. This area at the top and the area at the bottom. I emphasize top and bottom just because they are top and bottom, they actually have the same area up and down here. So when you combine two objects, this area becomes bigger. And the way molecules apply force is by bouncing into the wall. If you have a wall, then some particle will bounce into it, creating a force. If your area is twice as big, there will be twice as much of particles bouncing into the wall at the same time. The amount of particle bouncing into the wall is proportional to the area of the wall. So this becomes 2F if your area becomes 2A. Okay? Now, the force that air applies to an object depends on the surface of the object. Depends on the surface area of the object. If we want a property just for the air itself, we can look at the relation between the force and the area of this wall. We know that force acting on this wall from the air should be proportional to its area. So we call this number between them the pressure. Pressure will be something just about the air. The force that an air applied to the object depends on the area of the object. But if you want to describe just the property of the air, that property will be this pressure P, which will be the amount of force that air can act on an object per area. Okay? This is pressure. And if we use 1 Newton for force and meter squared for area, we call that a Pascal. That's the unit if we are describing pressure. We usually use Pascal, which is Newton per meter squared. Okay? Now, even though we are looking at fluids, our equation for a system which you worked so hard on your last homework still works because we are just choosing abundant particles to be our system. It doesn't need to be a solid, it doesn't need to be a fluid, it can be anything. So, if I look at a bucket of water and I choose this part of water as my system. This is like a cylinder. This cylinder has a length, let's say d for the depth of the water. There's area of this cap of the cylinder, and it's the same on top and on the bottom. So when we look at these systems, there are 3 forces acting on the system. One is the force from the top caused by the air. One is the force from the bottom caused by the water. And the final